All right. So let's get back to our perturbations. So at the beginning of the lectures, we went through all the physics, or let's say the fundamental physics that characterizes the behaviors of the universe, assuming it homogeneous and isotropic. And therefore, we studied dark energy, modified gravity, and all these kind of things. Later, the last bunch of lectures, we started to look into the inhomogeneous universe, because we know that it's composed by fluids, so there are various ingredients, for example, dark matter, radiations. They are fluids, and as such, they might have a sound speed. They have a sound speed which is smaller than the one of light, and therefore the sound horizon is within the Hubble horizon, okay? And this allows for oscillations, right? Macroscopic effects are in place. We have a pressure contribution which is non-negligible, and these contributions, these fluids, can oscillate. Then we also discovered that dark energy is a fluid. We can explain the expansion of the universe through a fluid which should be in the slow rolling phase, right? If we go back to the Klein-Gordon equation that characterizes the behavior of this fluid, it should be slow rolling, such that it behaves roughly like the cosmological constants, okay? But it's a dynamical fluid described by a Klein-Gordon equations, like matter, like radiation, okay? The Klein-Gordon equation is just the continuity equation for such a fluid. And being dynamical, it could have a sound speed which is smaller than the speed of light. And whenever this is the case, then also dark energy might be non-uniform across the universe. Therefore, we might have a larger amount of dark energy, so the values of the field is larger in one location with respect to another location. Okay? Same as matter and radiation. And to characterize these fluctuations, both for dark energy, dark matter, and radiation, and matter and baryons, we used a perturbative approach. So we started with the full equations characterizing gravity and characterizing the matter, the source of gravity, therefore the hydrodynamic sector, so we have the gravitational sector, the hydrodynamical sector, and we linearize the equations by introducing perturbations, right? And therefore, and then we focused on the perturbations only. The background we know, because that's the one that we characterized in all the first part of the lectures when we dealt with the homogeneous cosmology. Now we just focused on the perturbations, right? For example, we had density is equal to the density of the background plus a tiny perturbation, okay? Same for pressure, same for the velocity, which becomes the proper velocity with respect to the bulk flow of the universe, and the same is going to be for dark energy, okay? So, during the last lectures, we took the Einstein field equations. We massaged them a little bit by introducing new quantities, such, for example, this lambda, which is just the inverse of the K modes. Okay, remember the K modes characterizes the oscillation, the frequency of the oscillation of the various perturbations that are overlapping with each other, normalized with respect to the tilde, the fancy h here. Okay, so that's double factor times a. And then we also introduced, right, we had the velocity field, but we care about the amplitude of the velocity field, therefore we wanted to transform this velocity, which is a vector, into a scalar. That's why we took the divergence, of the velocity to have a scalar field to characterize with one equation instead of carrying three equations that are kind of analogous in the linear regime. And then, again, we just, from this divergence of the velocity, we computed this divergence normalized with respect to this fancy h. Okay? That's the only thing. Then we combined these two equations, and we got the Poisson equation in a relativistic regime, where you see that we have like the Newtonian component, that's the standard Newtonian component, but there is a relativistic correction here. Okay? Then we have the meta equations for hydrodynamics, and we got the continuity equation and the Euler equation, and again, as we did in the previous, as for the gravity sector, we introduced this quantity, and I recall you that with the prime, now these are derivatives with respect to n, okay? N is going to be our variable characterizing the time evolution of our fields. And you see that this set of equations is incomplete, because we have phi, then from the Einstein equation we also have phi equal to psi, to minus psi, that's the other scalar potential that that enters into the metric. And then we have radiation or matter, okay, characterized by this guy. Dark energy is missing. That's what we need to compute today, okay? So we are going to have a continuity equation for dark energy as well. And therefore, we need to evaluate the Klein-Gordon equation for dark energy. Okay, so let's get started. Dark energy as a fluid, which is a property, as I said, that allows for it to cluster. Good. So we have the usual characterization for dark energy. So we are going to have the effective equation of state. Then I need to distinguish with respect to the one to the matter, which might be radiation again, or proper matter, which is dynamical. Therefore, it can evolve as a function of the expansion factor, therefore as a function of time. It's going to have a pressure that might change, and it is going to have a density that it might change as well. So they are evolving dynamical quantities. Then, in this case, it's going to be, being a fluid is characterized by a sound speed, so the square of the sound speed, just using the definition, is just the perturbation of the pressure for our scalar field and over the perturbation of the field itself. Okay? That's what this guy is. And the field that we are going to characterize again is dark energy, which we linearize as well in terms of a background plus a perturbation of the background. The solution for this guy we know. We already solved that set of equations. Now we care about the perturbation, the phi, right? Therefore, we need to characterize our perturbative field. And how do we do it? Well, we know what is rho and p for dark energy, right? We are using an ideal fluid, so we are modeling it as an ideal fluid, as a perfect fluid, and we know that the density is going to be minus 1/2. Then we have the value of the field, the derivative of the value of the field, derivative of the value of the field. That's the usual kinetic term. And then we have a potential if dark energy is characterized by a potential which is non-zero. And the pressure, again, is going to be minus 1/2. We have the kinetic term, and then, as usual, we have plus, out of which, you see, we can get the equation of state. Now what we need? We need to characterize this field, that characterizes the perturbation of the field, okay, of dark energy. And therefore, what we do, we linearize, or we expand this expression in terms of these two guys. Therefore, we just plug it here, 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 and here. Keep in mind that here we have a contraction between these two terms, okay? We have repeated indices, and you have the metric there, right? So which metric are we going to consider? We are going to consider the perturbed metric. remember, we had G mu nu, which was equal to G mu nu at 0th order, so this would be the Friedman, Lametta, and Robinson-Walker metric, that's our background, plus the perturbation at first order, okay? So we are always keeping perturbations at first order. We plug them here, and then we keep only first order. Only first order terms, and they are delta rho v of h to the power of 2, so you see that this is entering to the metric. Then we have phi prime d phi prime minus phi prime to the power of 2, gravitational potential phi, again this is entering through the metric, minus the potential, the fluctuation, the perturbation of the potential, which is just the derivative of the potential, times the variation of the perturbation of the scalar field phi. That's because remember that v is a function of phi. Okay? And then the same for the pressure. So we're going to have the perturbation in our pressure for phi, for our field, for our dark energy, which is equal to that. So you see that's very similar to what we have here, except for the fact that we are going to have a plus. Okay, p, sorry, plus and minus, v comma phi, and then we have the phi. Yes. Okay, we call it equation E and equation B. And then what do we have? Well, we have the divergence of the velocity, because here is a fluid, and through the continuity equation, you know that we have the conservation whenever, you know, the fluid that we have in one region is moving to another region, okay? So for the time variation is related to a flux, okay? For the fluid in consideration. And therefore, we are going to have a divergence for our velocity field, so we're going to derive basically this guy, not for the matter component, but for dark energy. Same stuff, is a fluid as a matter and as baryons. And we just get this one, so you can read the gradient in Fourier space, right? IK, that's the gradient. And then we have just using the velocity from the energy momentum tensor of our fluid, because remember that this is characterized by an energy momentum tensor that contains velocities for the fluid, okay? So we get just from the zero component, 0E, okay? Remember that continuity equation is the first row equation associated to the conservation of the energy momentum tensor. That's why we have 0E here. For our field, divided 1 plus W field times rho field. Okay. Then here we have our perturbation of the energy momentum tensor, component 0E, that I gave you during the last lecture, in general for a fluid. So this is just the one of dark energy. And this can be written as lambda to the power of minus 2, the phi over phi. And we call it equation C. Then how else do we characterize our dark energy? Well, we can associate to it a mass, right? Well, Klein-Gordon equation, in which a mass characterizing this field comes out, okay? And this is just a definition, and is defined as the double derivative of the potential with respect to the value of the field. And then, you see, we are characterizing everything normalized with respect to this tilde h, this fancy h, which is just AH, okay, just a definition. we can as well normalize this guy in this way, such that we have nabla square divided m, that's for the field phi over our fancy h, and as well the potential. So it's convenient to also have this sort of renormalized potential with respect to the expansion function, v divided h to the power of 2. Yes, that's an h, not h bar, h tilde, okay? Good. So we have also these other parameters characterizing our field, and these very important equations, because you see, those are the ones that we're going to introduce in the Euler and the continuity equation. So these are completely generic. You see, whatever fluid we have, these are just hydrodynamic equations. So we can just plug in the equation of state W, the sound speed, and then the values for the perturbation. That's it. We have our dark energy. Okay? That is now characterized in terms of the potential and the mass of the field. So let's go for that. And what we do? We take equation 5. Therefore, we are taking the continuity equation, energy conservation law. Just write, well, it's written there, so I don't write it again. Then we plug, so we are going to plug in that equation A, B, and C. These three quantities, as I said. And then we can as well characterize h bar over h minus 1 over 2, 1 plus 3 W effective, which is coming from the Friedman equations. Okay, so from the Friedman equations, we have this expression that characterizes the derivative of this fancy h with respect to the equation of state parameters that we are going to enter there. Okay. So, and of course, I just going to use here we have the perturbation, but what we use, remember, is the perturbation with respect to the background. Okay. Therefore, we're going to have the perturbation of the field with respect to the value of the field itself at first order, right? Therefore, that's the background solution that we're going to have. So that's the new player. And whenever we do that, when we put together all these terms, we are going to get derivative phi dot dot plus 2 plus h bar prime over h, and here you can see the imprint of the equation of state of our dark energy. Then we have the phi prime plus lambda to the power of 2 plus the mass of our scalar field, the phi minus phi prime 3 phi prime minus psi prime plus 2 phi psi equal to 0, where we also introduced the Poisson equation. Okay, that's why you have these potentials that are popping up. That's the key expression that you need to account for. Okay, as usual, you see, is we have double derivative of the perturbation field, first derivative of the perturbation field, and then the perturbation field. And as you see, this is just what? This is an oscillatory expression, okay? So we have a damped oscillation with a damping term, and this shows you, yes, our guy can cluster, can have oscillation modes with a propagating speed, which is with densities that are perturbation that are propagating with a sound speed, and you know how m is referring to L can give you a clustering which is relevant or not. Okay? And this is the other key aspect that would allow you to distinguish dark energy from the cosmological constant. Because by construction, the cosmological constant is not an oscillating field. Remember, when we were looking at the Klein-Gordon equation, we were looking at the oscillation of the potential for dark energy, sorry, for the cosmological constant. The cosmological constant, yes, can be characterized with respect to a fluid, but is sitting at the minimum of the potential, there, just like that. It's not oscillation. It's not behaving as matter. Okay? But on certain scale and for some m, yes, it's oscillating slowly, so it looks like, you know, like dark energy. Sorry, as the, so dark energy can look like a cosmological constant, but it depends on these two guys and on the scale that we are considering. Okay? Good. Now what do we do? That's nice, but that's not the entire history. And that's not the entire physics that we use in characterizing dark energy. Because in this case, there are no interaction with anything else. We use the continuity equation, and that continuity equation was just coming from, is a conservation law, therefore we have T mu nu equal to 0. Okay, that's if we are using nu equal to 0, we have the continuity equation. Nu equal to 1, we have the Euler equation, right? These are these two guys here. There is 0 here. This fluid, characterized by this energy momentum tensor, matter in this case, or dark energy in this case, up to this point are not coupled to one to each other. What we can do now, we can introduce the coupling. Okay, so what happens whenever we introduce a coupling? Well, you already know what to do. We are going to introduce the coupling here. I just said it, right? And we have to do it for matter that we can split in two contributions, because we have dark matter and we have the baryons as well, with a coupling term which can be the one for dark matter associated to the field T of dark matter nu phi. Then we have the baryons, the mu, T mu nu for the baryons, and Q, which might be different in general. So we have the one of baryons. And T of baryons, that's the, and then the nu of the field. And then we have the one for dark energy. The mu T of our field, mu nu, is equal to what? Minus, remember that we have a total energy conservation, and therefore if there is an energy momentum exchange between the matter components and dark energy, the contribution on this side of the equation for the total energy conservation equation to work out must be negative minus the sum of these two guys. Okay? Therefore, we are going to have Q of dark matter, T dark matter, plus Q baryons, T baryons, and then the nu of the field. That's, these are our coupling equations. Here I'm kind of keeping it simple because I'm keeping the Q's as universal constants, and therefore they are not evolving as a function of time or location, but in principle they could depend on the potential itself, on the scalar field itself, on dark energy itself. And I recall you that phi is a fluid, and therefore it depends on time and space, because its values can be different in different locations. So that's the most general approach that you can have. Of course, now I'm going to simplify a bit the expression. I'm going to have only one Q, not depending on time, not depending on space. And I'm not going to do the entire derivation because it's utterly boring and completely not interesting, okay? But you understand already what's going to happen. This was our Klein-Gordon equations for our scalar field without coupling. This guy is all of that. Equal to 0 is that. So what do you expect? That these contributions are going to pop up here. Therefore, when you introduce coupling, you have exactly the same expression that I'm not going to copy. So this one is going to be a change. It's going to be the same. You're going to have additional terms here. Clean, okay? Just like that. And the expression is simple, but is complicated, but not too much. I write it here so that you have it. Omega E delta E minus 6 sum matrix of E QE 1 minus 3 WE omega E, and that should be the potential phi, and then I have minus 3 sum matrix E 1 minus 3 phi of E Q for the for phi. So that's the derivative, so that's component E phi, and then omega E, and then our value of the phi. That's when we introduce the coupling term. So you can recognize, so E, so I'm trying to write the equation in the most general case. So you see I'm expressing the potential, the gravitational potential psi to distinguish it from phi, but you know that in GR this is going to be minus phi. Okay, I keep it apart such that if you have some modified gravity theory and you are keeping these two separate apart, that's going to enter. So the other equation that now we keep it like this because of GR. Okay, it's anyway that potential, not phi. Okay, good. And what is E? E can be radiation or could be matter. So you see, you have these two symmetries. Therefore, it means that you have these two sets of equations twice summed together. One is going to be for radiation with its own sound speed and its own matter. Like we're splitting matter, then we have dark matter, and we have the variance as well. Okay? But remember what? For radiation, we had the trace of the energy momentum tensor that for radiation is 0. So you don't expect any contribution on this side for radiation. Okay? So only dark matter and variance. So you have this equation summed twice. Okay? Nice. Now, let's see, once we have our set of equations, one for gravity, one for the matter component, that up to this point can be radiation or matter or variance, we are going to simplify a little bit our expression. We are putting ourselves in matter domination with only dark matter is going to be relevant. Okay? So I'm going to characterize our universe using those set of equations for gravity, matter, component, in this case dark matter, as I said, we specify, we restrict our case, and then our Klein-Gordon equation for dark energy, including the coupling terms. Okay? Therefore, this is going to be the case that I'm going to consider. All right? Nice. Let's cancel everything. This one would be nice to keep. Well, let's keep this blackboard for the moment. All right. So, let's try to get a physical understanding of this expression. Okay, what are those terms doing? Okay, how is dark energy behaving? And for that, let's make some simplification, okay? Because this expression is long. There are a lot of various physical aspects that are occurring in this equation. You don't see it now, but there is screening there. You can have screening, and that's contained in this equation. Therefore, I'm going to split the concepts by making simplifications on different parts of the equations, okay? Such that we can explore different aspects of that expression, okay, in a clean way. So let's consider our simplification. And we are going to consider small scales, therefore our lambda tilde to the power of 2 much smaller with respect to 1. Quasi-static, quasi-static case in which that, yes, there is a time evolution, but it's extremely slowly. And all the time derivatives are going to be, there is a minus 2 working, are going to be negligible with respect to this guy here. There was a very important minus here, okay? Because you see that if this guy is very small, it means that this is going to dominate over all other terms, okay? All times derivatives are going to be small. So let's say that this guy is going to be away. We have a time derivative. This guy is ruling. And for the moment, we are assuming as well that lambda to the power of minus 2 is much larger than m as well. Okay? Later, we will keep this guy active, because this guy is going to be the one responsible for screening. Okay? If this is much larger than this one, then we can neglect this guy as well. Okay? And then what we have? Another time derivative, time derivative, time derivative, and then we have the potential, which is dominated by this guy. This is very, very large and dominates over this guy as well. Very simple. Okay? We are left with only one term on this side of the expression, and then all of these sumatories are going to be much simpler because we are going to consider dark matter only. Okay? And therefore, our expression, well, I'm also using, we are working in the Einstein frame, therefore also this expression is going to be true and relevant, and let me write it as well, that dark matter only, plus we have our field, our dark energy, okay? So, what are we left with? Very little, as I said, so we are going to have lambda to the power of minus 2, the phi, so that's just, what is it, this term here, all 0, 0, 0, 0, equal to that for dark energy only. And we get a minus 3q, that's the one of dark energy only, sorry, dark matter only. Q of dark matter, omega dark matter, and then we have the density contrast for dark matter. Look at this. How does it look like? Look at the Poisson equation. This is a Poisson equation. In general, whenever you have a Klein-Gordon equation, you know, with a coupling term there, and you work on small scales, and therefore in a quasi-static regime, you get a Poisson equation. What's the meaning of this? What's the meaning of this? That our perturbation of our field behaves exactly like gravity, like the gravitational field, because it obeys exactly the same equation. Okay? Look, forget about the relativistic case for the moment. Look at this expression and look at that one. They are identical. Okay? They express the same physics. They behave the same. They are going to have the same effect on the equation of motion of bodies. What's that? Modify gravity. Okay? Remember, during the previous lectures when we investigated the scalar tensor theories, coupling between dark energy and matter, remember that through conformal transformations, we could move from the Einstein frame, that's this prescription, in which we are using Einstein, the general relativity. So we are in the Einstein frame, and we have a coupling term. We can perform a conformal transformation in which we are going to remove these coupling terms and make them absorbed on the gravity sector. Remember, we were doing this sort of transformation from the Jordan frame to the Einstein frame and vice versa. Einstein frame with coupling, or no coupling, but modify gravity. And here, studying this equation, through the perturbations, you understand that the two are completely equivalent, and that's because of that. Okay? So you see, that's a very important physical point. Because you see that you start with a fluid with coupling, that's your physical interpretation of what's going on, of the entire business. You work in this regime, and you realize the fact that in the equation of motion, the contribution of this coupling is like the one of gravity. Okay? The two pictures are completely indistinguishable one from each other, because they give you exactly the same equation of motions in the end. Okay? And you see here clearly the connection, Klein-Gordon equation, with this approximation. You see that in this quasi-static limit, in the non-relativistic regime, below when for small lambdas, for high k's, you get the Poisson equation. Okay? What does it mean then? How do you interpret that if you want to kind of push it to particle physics? For example, in GR, we had our tensorial perturbation, two-polarization mode. This would be our beloved gravitons. But here we have an additional Klein-Gordon equations associated to a field. And therefore, we have another particle associated to a scalar field. That would be our modified gravity. So gravity is going to, in this picture, is going to be carried by these two particles. One associated to the perturbation of the metric, and the other, so our tensorial mode spin 2, and the other one to a scalar particle. This would be the direction for modified quantum gravity. Okay? Good. So let's go back to the fact that our perturb dark energy field behaves like gravity. How would this manifest itself into the Euler equation and into the Poisson equation? Well, you get a contribution which is like the one of the potential. Therefore, you're going to get a modification on the gravity parts of the Poisson equation and continuity and Euler equation, in which you go from the the gravitational potential without the coupling to an effective potential, which is going to be given by the Newtonian one, okay? Newtonian, I mean without coupling, plus Q, the phi. So what you are going to do, you can do the full mathematics, but it boils down to this exchange. So every time that you see Xi in this expression, here and here as well, remember that Xi is linked to phi, you just have to change this guy for these ones. Okay? Is this the end of the story? No. No, because if, remember that when we had coupling and we studied the continuity equation, it ends up that it appears that the mass of particle is changing as a function of time. Okay? What's the catch here? Remember that we have, like, through the continuity equation, with coupling, we have something like that. We could have interpret as the density of matter particle as the number density of matter particle, so that's a number of particles, with a mass which is not constant, but is evolving as a function of time. Okay, so we have that the density is getting diluted by the cosmic expansion, but we have an additional contribution which is given by the coupling Q phi. So there is this exponential that pops up. Okay, that's something that we derived. If we go at first order, we have m0, m sort of for very small q very small. Then we have e to the power of minus 3, 1 plus q phi. Okay? So the mass is changing and there is a q phi factor. Okay? What's going to happen in the Euler equation? Remember that the Euler equation is a force equation. It expresses simply Newton's force, okay? With a pressure contribution and a gravity contribution, okay? But the mass is changing. And the mass in that equation has the meaning of an inertial mass. And therefore, the resistance, if you wish to call it so, a resistance of matter to go through an acceleration once a force is applied to it. And you understand that if the mass is growing as a function of time, the acceleration is getting lower and lower, even though, for example, you apply the same force to the particle. How does it work like? How does it look like? It looks like friction. You are applying a force to the particle, there is the acceleration, but just because its mass is growing, and therefore it kind of gives more resistance to the acceleration given by the force. Okay? Just to see it like clear. So we are talking about Newton's law, which is this one. It's not F equal to m times acceleration. This one implies that the mass is constant. Okay, it's not anymore. It's the total the force in reality is the total derivative. Sorry, is the time derivative of the momentum. That's the definition of a force. And therefore, if you now introduce, the definition of the momentum as mv, that's where you get the a dot. Then you get the derivative with respect to the velocity, therefore you get the acceleration, and then you get the derivative of the mass with respect to the acceleration. This enters as a friction term in Euler equation. Therefore, when in the friction component of the Euler equation, that contains the H, okay, you need to introduce Q phi prime. Sorry? You have aim v dot, which is the acceleration, and then m dot and v. Ah, yeah, sorry, v. You're right. Thanks. Okay? So let's give a look at this point, because here there is a lot of physics. The rest is just, the following is going to be kind of better understanding also other terms, but the core is here. So Klein-Gordon equation for our field, for our dark energy field, which can fluctuate. We can introduce coupling just by introducing a coupling term between the matter component and the dark energy field. These terms are going to give you modification to the Euler equation as well as to the Poisson equation, because we start to use our brains and we start to investigate this equation in this limit. So we used the quasi-static limit for small scales, Newtonian, general relativity, and we end up by realizing that, yes, all of these terms are going to drop out. We are just left with this, which is a Poisson equation. Okay? Poisson equation that tells us that the effect of the fluctuations of dark energy on matter, therefore on the equation of motion of particles, is like the one of gravity, because the Poisson equation is the equation characterizing gravity, a scalar field, the dynamics of a scalar field. Okay? Nice. It means that out of this original potential, we need to include an additional term, which is given by the coupling, okay? Which is coming from here, this part of the equations. Then we have to forget as well that whenever we have coupling, also the mass of particle is evolving. Because when we evaluate the continuity equation, yes, we have a contribution due to the expansion of the universe that dilutes the density with a power of 8 to the power of minus 3, as 8 to the power of minus 3, but there is this exponential. We're now using Q much smaller than 1, just to not screw up all local gravity experiments. We end up with this expression, where we have this additional term here. And this tells us that, and this acts as a friction, because if the mass of the particle is growing, you apply an force to the particle, the mass is growing, and therefore the acceleration gets lower, because we have this term that is now active. This enters in the friction term. So what do we get? We have the Euler equation, the Poisson equation, the continuity equation, and our field equation for dark energy, in which we need to use these two new ingredients. These two new ingredients, let me now show it here. So, AV. Is it big enough? Can you see? Okay. Good. So, what do we have? We have our continuity equation. Is it the right thing? Yes. We have our continuity equation. We have the Euler equation. We have our Poisson equation. And then what do we have? We have our full expression describing the Klein-Gordon equation characterizing the behavior and the dynamics of dark energy, including coupling, okay, which is here. Then what we do? We work in the quasi-static limit, in which lambda is negligible, therefore our continuity equations simplifies to that. Continuity equation, Euler equation, coupling simplifies to that, so I'm just using these simplifications here for dark matter, as I said. I'm using general relativity, quasi-static limit, and on small scale, so the approximations that I was mentioning earlier, okay? And I'm using this expression, as I already said. And we get that, okay? That's in full generality, that's for the case that we are considering. And then we need to plug here the modification of the Euler equation that are going to have an impact on the friction term, therefore here, and this expression gains this guy here. Okay, the friction term, due to increased mass as a function of time. Then we have the fact that gravity is going to be modified, or let's say that we have the contribution of the equation to the equation of motion of matter associated to the dynamic of dark energy, and as we said, is going to affect the potential. Therefore, we have an additional contribution here and an additional contribution here. Okay, so these are going to be your modified continuity equation, Euler equation, and Poisson equation, including the coupling with dark energy. Okay? Then, just to show you a little bit, you know, another link a better link between the coupling terms and the gravity sector, we can get this modification and express explicitly the perturbation of phi with its own Poisson equation. Remember that we have this Poisson equation for dark energy, and we plug this guy here, and we get that. Okay? If we now have this expression in here, we can, you see, we have a lambda matter here, a lambda matter here, and we can group it together. Okay? If we do so, what do we have? We have a gravitational potential, which is like the Newtonian one plus a modification. Okay? You see? The effect of dark energy can be seen through gravity, or looks like, or is absorbed, if you want, on the gravity sector in the Poisson equation. Okay? Plus a friction term. You can have, you know, more complicated physical models by keeping the Q's independent, one from each other, one for baryon, one for matter. You can, you know, you can have a more generalized expression, but whatever you're doing, the modifications are going to appear always here, here, and here. Okay? These are the parts that are going always to be modified. The rest not. The rest is not going to be. Okay? And then what we can do? Well, once we have our expression for continuity, Euler equation, and our modified Poisson equation, we can put them together, as we already did in the previous lectures, and you find your matter perturbation equation, which is this one, okay? And gives you a full characterization of the matter density fluctuation, including dark energy, including coupling. Okay? And you see the coupling, in this case, appears here and here. And again, change your theory, make it more complicated, just these two terms are going to be modified. Okay? Then this is an expression which you typically, in full generality, do not have an analytical solution. Therefore, you have numerical solutions, but people found a very good approximation, which is this one. Okay, so people define the so-called growth rate, which is defined as the ratio of delta, so it's the time derivative, if the logarithmic derivative with respect to A of the logarithm of matter, of the fluctuation of matter. And it's a very, very good approximation, so it's not an explicit expression, but it's a good fit to the solution, to the numerical solution of this expression in full generality, and that's what you get, something very simple. Okay? F is just, so the growth rate, how structure is evolving as a function of time, as a function of the expansion factor, is just omega m time an exponential. Exponential, which is equal to 0.54 when you don't have any coupling, and you have a slightly different value whenever you have coupling. Okay? So that's your final solution. That's your final equation combining the three master equations, continuity, Euler equation, Poisson equation, including coupling, which has a very good approximation, which solution has a very good approximation, which is this one. Okay? That's it. That's all about, well, it's not all about dark energy and coupling, because let me conclude here. We have also this M that before we dropped out. Okay? Remember, if we go to the equation in full glory, where we were in the quasi-static limit, we neglected all the terms with times derivatives, all of that. We neglected this term because it's much smaller than this one, and we also neglected this M. But what happens when the mass of our scalar field is of the order of lambda to the power of -1? We cannot neglect it anymore. And if we don't neglect it anymore, this part of the equation is, survives. So this M survives. Therefore, our Poisson equation, characterizing the fluctuation of the dark energy field, is modified with this M. Okay? So here we have the Poisson equation for dark energy. We have our Poisson equation for the gravitational potential. We can put them together, okay? Because we have this delta M and delta M that links the two. So we just combine the two equations by plugging it in our modifications here, and that's the expression that we get. So the effective gravitational potential that we measure is like the Newtonian one, which is this guy here, plus a modification that is proportional to coupling. And it has a mass term in here, okay? So what is this going to give you? You realize that it's going to give you a Yukawa-like potential. That's screening. That's screening, that it occurs whenever the mass of the scalar field is not negligible anymore. Remember, in the past, we were always speaking at risk screening when the mass of the scalar field is relevant. Here you see it with a different angle. Okay? To have an even better understanding, let's get this expression, which is cosmological, so it's embedded in a cosmological environment for the density of the entire universe. Let's try to consider a point particle. Okay? So what we're going to do here is to transform this equation and characterize it for a massive particle, a point particle, which has a density given by the mass of the particle times a delta function. Okay? That's the dash, which tells us we have a particle of this mass, and that's located in this location in space. Okay? It's not extended. We can go, therefore, we have, and you see that everything works, so that this expression works, because whenever we integrate the density with respect to the three-dimensional volume, we should obtain the mass, right? And that's actually what happens, because this delta function is acting on the integral and is sort of selecting the mass. Okay? Then we can go to the Fourier space, and I don't discuss this expression, but the bottom point, so just substitute rho to the Fourier transform, and you realize the fact that also the density mode, K mode, in Fourier space is proportional to the mass of the particle. Okay, so whenever you see the density, you have to, for a mass particle, you interpret it as the mass, okay, the value of the mass. In the case of Earth, where the density is much larger with respect to the one of the background, we have now this expression that simplifies to that. So what we did, just use the definition of omega, which is this one, definition of the density contrast, which is this one, and then we just, this one and this one drops. We are left with the background that we are neglecting, because the density of the Earth, for example, or even a massive particle, whatever it is, a stone, is much larger than the one of the background. And therefore we neglect that, and we just have this ratio. That's the critical density, that the inverse of the critical density, which is this one. This is the mass, as we see here, and that's what the expression. You see, we have now an omega m delta k for the case of a massive particle. And we can plug it into here. We plug it into here, and we get this expression. Okay? That's in Fourier space. Let's go in real space, such that we have an expression for the potential, not with respect to k moles, but with respect to a radial distance. Okay? So that we have phi of r. Let's do that. Therefore, we go to the real space. Therefore, we apply the inverse Fourier transform to go from the Fourier space to the real space. This is just a matter of performing an integral, and you get this expression. Very familiar. Newtonian gravity for a massive particle plus a correction which is proportional to the power of 2 of the coupling constant. No coupling, Newtonian force. Coupling, we have a correction. Okay? And you see that there is a term which contains an exponential of minus m to the powers of r. So there is a radial dependency here. Okay? And this guy is a Yukawa potential. It has an expression of Yukawa potential. We have a damping. Okay? The larger is r, the smaller is going to be this term. And that's your beloved screening. Okay? The modification due to the coupling dies out at a certain distance, and the distance at which this dies out depends on the mass of the scalar field. Okay? So for very massive scalar field, you understand that this term is negligible. If the scalar field is small, then the effective contribution here is relevant and cannot be neglected. Okay? Coupling or modified gravity, depends how you want to interpret it, is in place. Okay? And it has an effect on the dynamics of the surrounding matter. Okay? That's it. That's all about dark energy as a fluid included in the perturbation. So here just a summary, because there were several steps, but that boils down to not so many concepts if you want. So we started by using our perturbation for the metric, the perturbation for rho, pressure, velocities, and the energy momentum tensors, and so on. Then we introduced new quantities, which is the density contrast for the fluctuations, and the divergence of the velocity field, such that we have a scalar field to track. We linearized our equation of motions, so we linearized the Einstein field equations, these four guys here. We linearized the conservation laws for the matter components that give us the continuity equation and the Euler equation. Then we combine them together, right? For example, the gravity sector to obtain a relativistic version of the Poisson equation. Then we just have a little bit of massaging of the equation. We went into the Fourier space. We introduced as a lambda hat and our V twiggled, which is basically a rescaling of the divergence of the velocity. And we just had the previous expression just mathematically massaged in this way, after which can be easily combined to get this expression. Okay, so we get like the perturbation, the dynamics of the gravitational potential by combining equation 1, 2, and 5, so for these two and these two, basically all of the four together. Then we have, again, by combining the dynamics together, the 5 and 6 together with the Poisson equation, we get our perturbation equation for radiation, if we are considering the relativistic case, or matter, for example, if we are considering dust. And we have these two expressions. Moreover, we have seen how we can use this expression for relativistic fluids, and for photons, for instance, to characterize the fluctuations of the cosmic microwave background. Okay? Then we had to introduce the dynamics of dark energy, which was not present there. So let's include the, that's something that we did today. We also introduced coupling, and then we realized that at the end, the effect of dark energy that, look, I would like you to notice, I'm not tracing here, because it's not an observable. We don't see dark energy, okay? we just see dark energy as an effect on the surroundings, on the universe and on matter dynamics. Okay? Here, there are the equations that characterize observable stuff, which are galaxies, that's matter. Okay? But we see dark energy indirectly through this equation. Okay? That induces modification here, here, and here. Okay? That's the entire story of linear perturbation theory. Okay? Small perturbations. In the next lecture, we are going up of one order. So we're going to do perturbation theory at second order. Okay? So we can have a small break, perhaps now 6 minutes, at 35 past midday. Okay?